our work on simple harmonic motion, and we're going to start thinking about the equations that we can use to describe the motion. To do this, you need to be familiar with the graphs from last time, so we'll just look at those briefly. So here we go. You should be familiar with displacement time graphs. This is the displacement time graph here. You should be recognizing the shape. It looks like a cos graph, showing that we go from a maximum displacement through the equilibrium position to a maximum negative displacement, and then that cycle just keeps on repeating. Then if we look at the gradient of this graph that tells us at each instant what the velocity is, we get a velocity time graph. So I'll move this out the way. Here we go. And we get a velocity time graph. And this should link quite closely to the analysis we did last time. So you'll see that when the displacement is at a maximum, the velocity is 0. And then as it returns back through the equilibrium position, at that centre point, it's going to be going at its very fastest, but it's heading in the negative direction, so we have a very large or maximum negative velocity. And we can follow that through and we get this velocity time graph, which looks like a sine graph, but a negative sine graph. It's been reflected in the x-axis. If we follow the same idea as how we went from displacement to velocity, and we look at the gradients again, we get that we start with a large negative gradient, which tells us what we know already about acceleration. We start with a large or maximum negative acceleration. You can think of this two ways. You can just look at the graph and see because of the steep gradient it's a large acceleration, or you can also think to yourself that when it's displaced the most, that's when the restoring force is at its largest. So the bigger the force, the bigger the acceleration. Newton's second law. But it's pulling it back towards the centre, so it's a negative acceleration to start. And we can't see it very well on my screen here, but if you look between these, you'll see that the displacement and acceleration time graphs are basically mirror images of each other. So we're going to use this and what we know about these shapes to see if we can come up with some equations that will let us describe the motion. Whoops. Okay, so I've started off with some sort of questions that I would normally ask in class. I'm going to move this out the way down here. So it's what do these graphs look like? Well, I've already said they look like trigonometric functions, sine and cos graphs. What I normally go on to ask is what shapes are linked to those functions. And generally, students come back with triangles, which is not the answer I'm looking for. Circles. Something to do with circles. So we're going to start trying to look at what the connection might be between circular motion and simple harmonic motion. And normally I'd set this up as a demonstration in class. I can't do that now, so I've got an animation instead. But what I want you to imagine is a circle, maybe a train track, and a model train moving round and round and round in a circle. And what I want you to do is think that what would happen if you set up a light shone on that train going round and round in circles that casts a shadow on the wall. What would the shadow look like? You don't have to think about it. I've got an animation. Here we go. Right, so here's my model train going round and round in circles, going around quite slowly right now. Now, that's not simple harmonic motion. It is periodic motion. It does repeat, but it's not simple harmonic circular because there's no restoring force towards a central position, right? And the acceleration and force aren't proportional to the displacement because that just doesn't make sense. But if you look at the shadow of the train, which is jumping around very quickly, you would find that it effectively comes to a stop at one end, speeds up, gets faster and faster and faster as it moves through this central position, then slows down, slows down, slows down, comes to a stop, speeds up, speeds up, speeds up as it comes back. It's like it is obeying simple harmonic motion. There isn't a force that's proportional to the displacement, but the acceleration is. So, what we can say is that if we think about one component of circular motion, so in this I might call this the x component, that appears to obey simple harmonic motion, as long as we're talking about acceleration being proportional to displacement. Now this might be handy when we come to analyse this. I've got one more little animation of this which I think is quite nice, that gets rid of the model train. I'm just going to see if I can scroll this up a little bit. Okay, so it's not very scaled very well on the page, but I've got this red dot going round and round in a circle here, and the blue dot is just the x component of that motion. And although the red dot's going round in a circle, the blue dot is behaving as if it's obeying simple harmonic motion. Now, being that we are able to describe the motion of things going in circles, we should be able to use that to help us come up with some expressions to describe the motion of this blue dot, of something obeying simple harmonic motion. So, let's try it. Now, normally in class people get a bit worried at this stage. Some people have heard of simple harmonic motion, so this is my little bit to gee us up. This is going to be easy. Why is it going to be easy? Can we describe the motion of something in a circle? Yes. Is periodic motion, or simple harmonic motion, just one component of circular motion? Pretty much. Not exactly, but pretty much. And I can't even remember what I put under here. Can we therefore use the equations we already know to describe simple harmonic motion? Hurrah! So let's do it. Now, you do need to start by thinking back to circular motion. A couple of the definitions. I'll run through it quickly here, but you might want to go away and do a bit of circular motion revision yourselves. So, next step. We've got to we haven't got to introduce, we've got to reintroduce the concept of angular velocity. Now, angular velocity was the rate of change of angular displacement. This thing, theta, is our angular displacement. It's in radians, remember, times in seconds. Angular velocity is therefore radians per second. And that's fairly useful. What's going to be very useful is the way that we were able to determine in circular motion what the angular velocity of something was. And if you remember, often the questions would be things like a geostationary satellite orbits the Earth and it's at a height of this, that and the other. What is the angular velocity? And you would use the fact that you would know the time it took for a complete orbit. That wasn't a good explanation. But what I'm getting at is that there is a sort of a handy version of this equation where instead of considering a particular angular displacement, we just consider a full circle. So we consider, well, if we were using degrees, we'd say 360 degrees, but we're not. We're using radians, and you know that there's 2 pi radians in a circle. So the other way of determining omega is by knowing the time period for one complete rotation. So, linking to the last equation, omega is theta over t. So we substitute into that 2 pi for the angle that we turn through, a full circle, and capital T rather than little t to represent the time period. That is something worth noting and taking down. In fact, on the next slide, I've got the sort of important bits. So if you know in circular motion what the time period is, you can always determine the angular velocity. For some reason I rearranged that here. I have no idea why I did that. It's of no use to us right now. This is the important bit. Also realising that time period is 1 over frequency. So frequency is something that might come up. So you might sometimes have this written this way, where omega is 2 pi f, because frequency is 1 over time period. Okay, so there are two basic things, and then there comes a problem. Because we're going to start talking about simple harmonic motion. And in simple harmonic motion, if you just watch some, I don't know, let's have a pendulum that's oscillating backwards and forwards like this. There isn't an angular velocity there that you could measure. But what you can say is that simple harmonic motion does have an angular velocity, but the angular velocity you're talking about is, I'll go back to this animation. Where's it gone? I'll scroll this up a little bit. Right. The angular velocity of the blue dot is the angular velocity of the circular motion that has one component of it that is behaving like the simple harmonic motion you're interested in. Now, I think that's probably a bit of a garbled explanation, so I'm going to show you some more things and see if it makes sense as we go through it. Basically, what we're going to be doing is determining the angular velocity of the simple harmonic motion. So, now you're going to need a pen and paper. If you haven't had one already, you definitely need one now. And we're going to consider this. So I would pause this for a second and draw this out. We're going to have an object, that's this little dot here, and this is moving around in a circle with angular velocity omega. The radius of the circle is r, and at the moment its angular displacement is theta. And what we're going to look at is at any point through its motion, how far is it displaced along this x-axis? The reason we want to do that is that if we then look at this animation over here going back and forth, the expression that tells us this point here will be able to tell us the position of the blue dot as the simple harmonic motion is taking place. So stop and pause and draw that for a second. Okay, so looking at this, knowing that this is the radius and this is the angular displacement, you should be able to see quite easily that this position x is just equal to, or the length of this side anyway, is just equal to r cos theta. But theta is going to equal omega t. Remember, omega was theta divided by t, so you rearrange that, you get theta equals omega t. So at any instant in the motion, if we've started here and moving round, we can say that the x displacement will be r cos theta cos omega t. Sorry, I said that wrong because my phone just went off. So the x displacement is r cos omega t. Now that's fine if you're analysing a circle, but in simple harmonic motion, there isn't a radius, there's an amplitude. And in fact, the maximum x position is when the amplitude is the same as this radius. So we change this equation. I've done that on the next slide. For the circle, x is r cos omega t, but because we're talking about simple harmonic motion, we have an equation for our x displacement. The displacement at a particular time is equal to the amplitude multiplied by cos omega t. And if you plotted a graph of that, it would look like the displacement time graph that we came up with earlier. Now, I'm going to stop this here and then make a second video where we're going to move on from the x displacement to velocity, acceleration, and beyond.